Welcome back to videos for section 4.2. I'm going to unpin this page real quick and get out your notebooks. And what we're going to be doing in this video is graphing logarithmic functions. And a property we're going to exploit is the visual graphical property relationship that exists between functions and their inverses and their graphs. And remember that functions and their inverses are reflections of each other across the line y is equal to x. So if I have this xy coordinate system, boom, boom, there's a line y is equal to x. It's this line that goes up like this, 45-degree angle through the origin. And that's the line of reflection between a function and its inverse. So say I have a function that looks like this. Here's our exponential growth function. Boom, 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 boom. Its inverse function, to get its inverse, we reflect it, this function, across the line y is equal to x, and then we can get its inverse function. That looks something like that. We're going to formalize a process for just generating graphs of these logarithmic functions, and we're going to start with what we know, and what we know are how to graph exponential functions. So the first graph we're going to try doing is graphing f of x is equal to log base 2 of x. Well, what's its inverse function? Well, this is equal to y, and so the inverse function is going to be y is equal to 2 to the x. The base stays the same. So if we were to use the process we did in the last video, we do log base 2 of y is equal to x. So 2 to the x is equal to y. Boom, there's our inverse function. So we find that inverse function, and now we're simply going to create a table of points for the inverse function, because it's a lot easier for me to come up with values for exponential functions. So I'm just going to create a table of points, and I'll create another table of points here, and I'm just going to graph some points. And so the table on the left is going to be my inverse function. Y is equal to 2 to the x. So this is y is equal to 2 to the x. And I've got x. And over here I have x, and I'm going to have log base 2 of x. So they're inverses. So I'll do -1. My favorite values, -1, 0, 1, and 2. 2 to the -1 is 1/2. 2 to the 0 is 1. 2 to the first is 2. 2 squared is 4. I could do 3. 2 to the 2 cubed is 8. Now, remember inverses, domains and ranges interchange. So 1/2 and the inverse is going to go to -1. 1 is going to go to 0. 2 is going to go to 1. 4 is going to go to 2. And then 8 is going to go to 3. And I'm just going to plot these points. So I come over here to this page, and I'm going to plot some points. And I say, okay, 1/2, I go over 1/2, and then I go down -1. So I have a point right there. And then I go over 1, I go up 0, I go over 2, I go up 1, I go over 4, I go up 2, I go over 8, I go up 3. It might have been helpful if I'd had another point like -2. So -2 would go to 1/4. So I have 1/4 here, and that's going to go to -2. So if I come over 1/4, I'm going to go down to -2. And now what we have, we can connect these dots, and this function is going to be slowly increasing. Remember, our exponential function has a horizontal asymptote that is equal to y is equal to 0. So we have the black function over here, we have this horizontal asymptote that looks like that. When we reflect this horizontal line that is the x-axis across the line y is equal to x, we end up with a vertical line. And we're going to have a vertical asymptote. You can see that, kind of start seeing the asymptotic behavior of these points in our logarithmic function. But as x gets smaller, well, over here in the exponential function, as x gets negative, these values get really, really small, but they never approach 0. So our inputs to our logarithmic function are going to be really, really small numbers, but they're never actually going to hit 0. So we end up with this vertical asymptote that is the y-axis. So x is equal to 0, which is our y-axis. That is the vertical asymptote for every single logarithmic function before it gets translated. So we've got this vertical asymptote that is the y-axis. So VA is x is equal to 0. And yeah, so as x, so one thing I want you to notice is that since the y-axis is the vertical asymptote, we have to exclude x from the domain. So x can't equal 0, nor can x be negative. There are no negative numbers. So our domain ends up being all numbers that are greater than 0. So we don't allow any negative numbers, and we don't allow any zeros as inputs into our logarithmic function. And you can see that if you play around with the point values in your exponential function, your logarithmic function. If we have -3, that's 1/8. If we have -4, that's going to be 1/16. And then we flip-flop them over. 1/16 goes to -4. 1/8 goes to -3. These values, the only inputs that we're allowing are these outputs of our exponential function. Since the outputs of our exponential function are never negative, we don't ever allow negative inputs into our logarithmic function. Nor do we allow a 0 input because this output of our exponential function is never 0. So that's how we end up with the domain, a vertical asymptote, that's the y-axis, and a domain numbers greater than 0. Notice the range. Y can be all real numbers. So you can write that as -infinity to +infinity. End behavior. Well, the limit of f of x as x goes to -infinity is, well, it doesn't go to -infinity. It doesn't happen. Instead, we can write here at the left end of the function the limit of our function f of x as x goes to 0, because that's as far as this function is going to go to the left, and that's going to be -infinity. As I trace this function, boom, 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 as I'm approaching 0, my function is just like going down, 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 just like in the Bruce Springsteen song. Now, in the other direction, the limit of f of x as x goes to infinity, trace the function, our function is growing. It's actually eventually going to hit +infinity. It's increasing without bound, but it's just increasing at a slower rate than our parent exponential function, than our quadratics, than our cubics, but it's still growing. It's just growing at a far slower rate. And notice the behavior. This function is increasing from 0 all the way to +infinity. That's what our parent function is doing. It's nowhere constant, and nowhere is this function decreasing. But notice that as it's increasing at a decreasing rate. So the rate of growth, it's like really crazy big here. Picture those tangents to this curve. Crazy high slopes of those tangent lines here. Then as our function grows, the slope of that tangent line gets shallower and shallower. So we're increasing at a decreasing rate. But we're still increasing at a decreasing rate. But increasing at a decreasing rate is still increasing. So that's how we graph. I use the graph of exponential functions to help me come up with the parent function graph of a logarithmic function. We'll do that well, let's have a look here. There's some other, depending on the base, that determines like what the graph of the logarithmic function looks like. If the base is greater than 1, it's going to be logarithmic growth. And here, the red curve is log base 10 of x, the common logarithm. The yellow curve is natural log of x, so log base e. And you can see both of those are increasing functions. And notice there's a point that all of these graphs go through. That's a very important point. All logarithmic functions that have not been, logarithmic growth functions that have not been translated go through the point 1, 0, which is really, really nice. And they haven't been dilated either. Next video, I'll show you guys how to graph a logarithmic function that has a base that's between 0 and 1.